Okay, good day, everyone. My name is John Kearney. I'm with AMETEK Process Instruments, and I'll act as your moderator for today's webinar on reliable combustion control for thermal oxidizers, which will be presented by Tim Talon and Jochen Geiger. We're certainly excited to share some interesting and educational information on combustion measurements in thermal oxidizers with everybody today. But before I turn the presentation over to Tim and Jochen to make introductions and share their content, I just wanted to cover a few logistic items beforehand. We are recording this session, and just to minimize background noise, we just ask you to make sure that your phone or your computer microphone is muted. We do want the session to be interactive, so if you have a question, you can use the chat feature in Microsoft Teams. For those who maybe aren't familiar with this particular platform, in your Teams window, you'll see an icon on the top right area of your screen that looks like a quotation. If you click on that, a chat box will appear on the right-hand side of your screen, and you can feel free to type your questions in the chat. I will moderate that, and at an appropriate time, we'll either interrupt or wait till the end to ask the speakers the question so that they can address that for you. As I mentioned, we are recording the session, and it will be available on our AMETEK Process Instruments YouTube page within the next few days, and I will posted a link to that page already in the chat window. Just as a overview, this webinar is sponsored by AMETEK Process Instruments. We are a worldwide manufacturer of process analyzers and instrumentation, and serve a wide range of markets from environmental monitoring to hydrocarbon processing, including things like refining, petrochemicals, power generation, natural gas, and many others. So our manufacturing engineering activities take place at 3 different locations that we have in North America. And we do have a global sales and service offices around the world. In fact, Jochen is joining us today from Germany. We're also supported through a wide network of sales representatives and distributors and service technicians around the world as well. So with that, I will turn the presentation over to Tim and Jochen, and off you go.
Thank you, John. And just to introduce myself, so my name is Tim Talon. I'm the Combustion Product Manager here at AMETEK Process Instruments. I represent the Thermox and Clean Gas product lines. And prior to this role, I had quite a bit of experience designing thermal oxidizers, and really see this presentation is meant to really join those two together. Where does oxygen measurement meet? Where does reliable combustion and oxygen measurement meet reliable thermal oxidizer control? So we'll talk about that. And I'm also joined here with Jochen Geiger. If you want to introduce yourself real quick, Jochen.
Hi, good afternoon or good morning to everybody, wherever you are. My name is Jochen Geiger. I'm with AMETEK for the last couple of decades. So I'm happy to see so many people join our webinar about this interesting topic. So we will go through that together. I will put a couple of comments in. So John say, I'm staying in Germany. My house was safe, more or less safe over the last 2 weeks. So let's hope, keep fingers crossed that this will continue. So back to you, Tim. I'll switch off so people should see me. I'm real, so I'm here. I'm not a computer. So let's enjoy together and have a fruitful discussion at the end of the presentation.
Thank you, Jochen. Thanks for joining. So again, the focus of today's conversation will be reliable combustion control for thermal oxidizers. So let's talk a bit about the agenda for today. So we'll talk a little bit about how thermal oxidizers, how they work, how they're different than some other pieces of fired equipment that you might be familiar with. We'll talk about different markets that thermal oxidizers exist in. We'll talk about how they work. We'll talk about the importance of the oxygen measurement, specifically the excess oxygen measurement, which we'll talk more about that later, but is a pretty critical specific measurement for thermal oxidizers. We'll also talk about relevant combustion measurements, and then we'll talk about how chlorinated applications some considerations around chlorinated applications. So to start off, why do thermal oxidizers even exist? Well, they exist for the full reason of emission control, to reduce air pollution, and doing that by burning the volatile organic compounds, the VOCs, or the hazardous air pollutants, the HAPs, in the waste stream. And they do that specifically through some type of combustion or high temperature thermal oxidation process, hence the term thermal oxidation, high temperatures, and oxidation with reaction with oxygen. Now, thermal oxidizers differ from the conventional term of incinerators just because they're a little bit more specific. Thermal oxidizers burn only gases and liquids, whereas incinerators could burn solids, they can burn other types of solid type wastes. So a thermal oxidizer is much more specially designed, and that's why it's especially designed for these gases and liquids, which is why we're talking specifically about thermal oxidizers, as opposed to incinerators, which could burn anything and have any type of variable waste stream. Now, that being said, when we think about measurement objectives, it's always important to think about safety. So monitoring for safe and incomplete combustion. We want to make sure that you're operating with complete combustion as opposed to unburnt waste or other forms of incomplete combustion. It's absolutely critical to have the correct air-fuel ratio, making sure that you have enough air to fully oxidize any of the waste gas possible with that's directed to the thermal oxidizer. And also, again, having sufficient oxygen and monitoring that so that you can have high destruction removal efficiencies. We'll talk about DOE throughout this presentation, but it's absolutely critical to have sufficient oxygen so that you have a high removal of the waste gas compound.
We will also talk about this air to fuel ratio a couple of times during the presentation.
That's right, Jochen. We'll talk directly about that towards more the middle of this presentation. So some of you may be very familiar with fired equipment, and specifically fired heaters. Fired heaters have a very specific function, and thermal oxidizers have a very specific function. So let's talk about that for a second. So a fired heater, as you may be familiar with, is designed specifically to heat a process fluid. So you have a whole bunch of tubes of different sort, and those tubes have filled with some type of fluid that you want to heat up for later on in your process. So you'll most often see multiple burners fire natural gas operating at relatively high temperatures, and you'll have a radiant section for the tubes to be heated up from both the heat of the flame as well as the radiant light from the flame. You'll have some type of transition zone for the convective section, and then out to the stack. So that's primarily a fired heater. The purpose specifically designed around heating some type of process fluid. Now, a thermal oxidizer, on the other hand, is designed...
And Tim, before you continue, just let's comment. We will do later this year a specific presentation about the safety aspects on fired heaters in the process industry. So there is a couple of things which we will partially cover today because it's more or less the same topic, but we will have a specific webinar for safety aspects on fired heater later in the year. Okay, let's go on with thermal oxidizer.
Thank you, Jochen. That's right. That's right, Jochen. So later this year, we'll have a secondary presentation to focus more on fired heaters, but certainly you can see how there's a big difference already. So fired heater designed specifically around heating process fluid. Now, a thermal oxidizer, on the other hand, is designed to control emissions. Typically, there's one burner, and that burner could fire natural gas or waste, or oil. If there's a high enough heating content within the waste, you could absolutely direct waste gas through the burner. Typically, the combustion chamber is lined with refractory. There's no coils because it's not intended to heat any process fluid. It's intended just to keep the chamber hot. The temperature can be anywhere between 1650 degrees Fahrenheit, 900 degrees Celsius, all the way up to, in some cases, it can even go up to 2200 degrees Fahrenheit. So it could be very hot, depending on what you're trying to burn and what type of waste gas you're trying to eliminate. And depending on the application, you'll have some type of downstream equipment for heat recovery, for example, or something for corrosives, because thermal oxidizers can certainly handle corrosive applications. So that's just a brief overview of how they're different from fired heaters and other forms of fired equipment. Now, when we go to think about where do thermal oxidizers exist, I want to be pretty clear that thermal oxidizers exist across industries. I mean, if you think about it in a refinery, there's gas thermal oxidizers, there's catalytic crackers. There's also a lot of different applications throughout chemical plants. Anything that has a a waste gas byproduct, whether that be a vent stream or a chlorinated hydrocarbon waste stream or a nitrogen-bearing compound, or even wastewater for like acrylonitrile, all of those different types of waste streams can be directed to a thermal oxidizer to thermally oxidize and eliminate the waste compounds before going to atmosphere. I mean, the whole purpose of a thermal oxidizer is to eliminate hazardous waste through incineration and thermal oxidation, and you'll see that throughout the chemical industry. But in addition, not just the chemical industry, you also see it in pulp and paper mills through non-condensable gas emissions. You also see them in asphalt plants, landfill gas, carbon black production, pharmaceuticals. So think about where your process might have some type of waste stream, and chances are it may very likely be incinerated, especially if it's high concentrations. It may be thermally oxidized through a thermal oxidizer. So a lot of applications and across industries. Now I want to take a moment to talk a little bit about the waste gas itself, because the waste gas derives much of the design of the thermal oxidizer. And so in a general sense, there are two scenarios. There's the contaminated air scenario, and then there's a highly more combustible waste stream compound process stream. Now, for contaminated air, it's basically contaminated air. It has trace amounts of contaminants. The airstream itself may not be combustible or have any type of combustible value, primarily inert, and it most likely has sufficient oxygen to use to mix with the waste gas compounds for oxidation. So from that perspective, typically a contaminated airstream does not require an oxygen measurement if it has high enough oxygen concentration. So if it's just generally air, 21% oxygen, generally those types of devices don't necessarily need an oxygen measurement because they have such high amounts of oxygen in that process stream. But for a standard waste gas stream, whether that be gaseous or liquid, you could potentially have very high concentrations of contaminant, so much so that it could actually be flammable. And in those cases, if it is flammable, you could use it as fuel and inject it through the burner for just for the initial injection into the combustion chamber. Or if it's more inert, you can also inject it downstream through a separate nozzle. But in those cases, you would absolutely require an oxygen measurement so that you can control the proper air to fuel ratio at the burner and with secondary air, which we'll talk about more. But really, it depends on the type of waste that you're looking to thermally oxidize in order to have the right design to meet that waste removal. Now, if we talk about contaminated airstreams, there's two different types of generally there's two different types of thermal oxidizers. There's a couple exceptions, there could be a couple more, but generally what you'll see for a vast majority of contaminated air applications is a regenerative thermal oxidizer. And generally in these cases, you could have 2 media beds, it could have up to 3 media beds, it could have even more media beds. But basically it has a special valve configuration that alternates where the waste gas is injected. And as waste goes in through one, you could have, it becomes preheated by this media bed. It enters into this high temperature area with a burner to remove some of the wastes and compounds. And after it goes through this area, it goes back through the media bed and with proper destruction removals, and then out the stack. So it has a combination of valves that alternate, and then once this valve closes, the other one will open and they'll alternate, so that you always have the waste gas coming in through the hot media bed and then the heat transfer out. So the benefit of a regenerative thermal oxidizer, an RTO that they call, benefit of an RTO is that it has very high thermal efficiency, 90% to 97% thermal efficiency, and that's because basically you have this constant heat transfer between media beds. And the thing about that is it has relatively low destruction removal efficiencies, because every time you switch open or close these valves, part of that waste gas doesn't get oxidized. It doesn't see the media bed, and so that's where you get the bulk of your emissions. Is actually not what's in the combustion chamber, but rather the switching of the valves. I don't know if you can kind of see here, but there's two valves here. As these valves open and close, then you have more or less opportunities for waste gas to avoid the media bed and go out to atmosphere. So that's the principle around a regenerative thermal oxidizer.
Tim, can I interrupt you for a second on a question? There was a question on this slide.
Yeah.
Are there catalysts in the media beds?
Are there catalysts in the media bed? No. It's actually just a ceramic material that is used for high efficiency heat transfer. The bulk of the actual incineration in waste removal actually comes from the heating of the combustion chamber itself. Good question.
Okay. And then there was a couple of questions that span the last couple of slides. One was, where is the flame temperature usually measured inside the combustion chamber?
Oh, we'll get to that.
Okay.
It's measured downstream right after you have proper residence time.
All right.
We'll get to that.
And then there was another question. Okay, there was another question on our thermal oxidizers followed by waste heat boilers for energy optimization.
Yes. Yeah, it depends on the size. Generally above 10 million BTUs per hour, you'll consider a waste gas boiler. We can talk about that later. That'll be additional slides, but good questions. Yep.
Okay, and then last one for the Jochen is several plants prefer oxygen along with combustibles or oxygen along with hydrocarbons. Which is a better way to monitor the air-fuel ratio?
So ultimately, the air-to-fuel ratio comes back to the excess oxygen measurement. And so ultimately, if you want to control your burner, I would say through the excess oxygen measurement, which we'll talk about that later as well. And the thing about that is with excess oxygen, combustibles helps for confirming whether or not it's incomplete combustion. Excess oxygen will tell you will better correlate with excess air. It will better correlate with the excess. It will account for. We'll talk about that later. I don't want to go too much in that because we'll actually talk about that.
Okay, that's fine. No
These are great questions, everybody. These are great questions, and these will certainly come up. And we'll have time at the end for additional questions if I didn't answer it thoroughly, but we'll definitely cover those. Just to make you aware, the other form of contaminated air thermal oxidation is through like a catalytic oxidizer. In this particular case, you do have a catalyst. For an RTO, it's much more like ceramic media, just for the heat transfer. For the catalytic oxidizer, what you have is the waste gas coming in through the tubes. Okay, so they're getting preheated through the tubes. You preheat your waste gas, and then they go through the various various catalyst beds for the waste removal. So, and then obviously that hot air, that hot media, hot waste gas or products of combustion go back through the chamber and then out the stack. So basically, you have the waste gas preheated. You go through various catalyst beds and then heat transfer back. So much, it has medium thermal efficiency compared to a regenerative thermal oxidizer, but much higher destruction removal efficiency because you're not, basically competing against alternating valves. But that's what we would consider for a contaminated airstream. Generally, they don't necessarily need an oxygen measurement because they're contaminated airstreams. Effectively, there's enough oxygen present in the stream naturally for full combustion. Now, where we're going to spend most of the focus of today's presentation on is around direct fired and recuperative thermal oxidizers. Now, the thing about them is they can be in many different configurations, single stage, multi-stage, depending on what the design is. Designs for lower NOx, designed for different waste streams. You can introduce the waste gas through the burner or downstream through a nozzle like I talked about before. And basically, it's able to handle waste liquids, waste gases, and they're highly customized. I mean, when I used to design thermal oxidizers, they were very highly customized depending on the size of the waste gas. I mean, the volume of waste gas, the components in it, and very high destruction removal efficiencies. I mean, we're talking 99.9% destruction removal efficiencies. So we call 4 nines destruction, very high destruction removal efficiency. And then with a recuperative thermal oxidizer, it's the same as direct fired, except it includes some type of heat recovery. Now that could be we'll talk about that later as well, but that could be a boiler, that could be a waste heat exchanger, it really depends on what you're trying to achieve. But let's talk about some of the primary elements of a thermal oxidizer. Every thermal oxidizer should have these components, especially the direct fired ones. So everyone will have a burner of some sort, and that burner can fire fuel, and if the waste gas is combustible enough, it can go through the burner as well. The burner can be fired horizontally. It can be fired, both of these cases it's fired horizontally, but it can also be vertically up fired, vertically down fired. It really depends on what you're trying to incinerate. You could also, depending on the waste gas, inject downstream as well. So it's very possible to inject waste downstream, depending on what you're trying to, the waste compound itself. You also have a combustion chamber. That combustion chamber operates hot, so 1600 degrees Fahrenheit or more, 900 degrees Fahrenheit C or higher. And then you also have a oxygen measurement towards the outlet of the combustion chamber, as well as a thermocouple. And the thing about that is these are absolutely critical for control. We'll talk about this later as well, but you'll have them right towards the outlet of the oxidizer chamber, just to make sure that you have sufficient oxygen to control your air inlets. You also have some type of PLC or burner management system to control the burner and the air-to-fuel ratios, and then also you'll have a fuel skid, obviously, to control the fuel before you go into the oxidizer. So, some type of control valve scenario, some type of a fuel skid, and then some type of stack. So that's the general overview of the elements of a thermal oxidizer, just at the bare minimum elements.
Tim, I think we need to talk about this 25% excess air. Do you mean excess air in the way of percentage or in the way of part of the air fuel to the combustion chamber? We have to go a little bit in detail for that point.
Yeah, that's a great question, Jochen. I think this is also pretty under-discussed, to be honest. So generally, the thermal oxidizers operated between 2 and 3, maybe a little bit more, maybe 2 to 4% oxygen on the outlet, and that's excess oxygen on the outlet. But when we specify the burner has to operate with 25% excess air at the burner. So that's a great question. When we talk about excess air, we're talking about excess air at the burner. So we need more air than stoichiometric, the ratio. We need more air than we need excess levels of air in order to fully oxidize and have enough oxygen present, so that we have 2 to 3% oxygen on the outlet. So that's a great question. Does that answer it for you, Jochen? Okay. So that's the idea. That excess air relates to the burner itself. Okay. One thing I want to make clear is that being that thermal oxidizers are so customized to the application, your application may have very specific elements added to it. So if you have a nitrogen-bearing compound, you could have a reducing chamber, which I'll show you in the next slide, in a future slide. But you could have a reducing chamber in order to remove nitrogen-bearing compounds. If your burner is generally above 10 million BTUs per hour, you would also consider to have some type of waste heat boiler for heat recovery. Absolutely an option. Alternatively, you could consider heat exchanger depending on whether or not it makes sense to preheat your waste gas, and if that impacts your oxidol, you'd have to consider that. But generally, there's also the option for heat exchangers for heat recovery, or flue gas recirculation for cooling the air, for additional options for cooling the flame and lowering NOx. Depending on the size of your thermal oxidizer, you may also consider a induced draft air fan. There may also be one at the outlet, and that would be to pull the full suction of the products through to the stack. So you might also have like an induced draft air fan right before the stack to pull all the products of combustion through the equipment before it goes to the stack. And then if you have particulate or chlorinated compounds, you might need additional equipment. Say you have chlorine or sulfurs, you might you might have a spray dryer absorber or a scrubber mist eliminator. If you have some type of particulate, you might consider electrostatic precipitator or baghouse. And if not a concern downstream, you might also have SNCR or selective non-catalytic reduction or selective catalytic reduction at the back end. So different ways to approach a thermal oxidizer, a lot of application-specific elements to consider. Now, a thermal oxidizer operates on what we call the 3 T's of oxidation. So obviously the objective of a thermal oxidizer is to fully remove and eliminate and destroy the waste gases in the waste compounds in the waste stream. So in order to do that, you need the 3 T's of oxidation: temperature, time, and turbulence. Let's go into that. So for temperature, when I say temperature, you need to make sure that you'll have a combustion chamber that operates typically between 1650 degrees Fahrenheit, 900 degrees Celsius, or higher, in order to fully to operate hot enough conditions. But that hot condition is dependent directly on the auto ignition temperatures of the constituents in the compounds within the waste stream. So your combustion chamber temperature is dictated by the auto ignition temperature. So that's the first T of, you need to have sufficient temperature to fully unlock that auto ignition temperature reaction. That's the first thing, auto ignition. Now the second thing, time. Now when I say time, you need sufficient volume of chamber in order to fully oxidize the waste compounds. Now this could be a half a second. Generally it's about 1 second residence time for 4-9 destruction, but that's a general rule of thumb. But you need sufficient residence time for those compounds at high enough temperature in order to fully oxidize them. So generally you could think that the longer the chamber, the higher destruction removal efficiency you'll have. So that's the second T, is this residence time. And the last T of oxidation, last of the 3 T's of oxidation, is turbulence. And turbulence specifically refers to the mixing and velocities within the combustion chamber, and ultimately turbulence with oxygen. It's 100% critical to have sufficient oxygen and have that mixed with the waste gas at high temperature with enough time in order to fully oxidize the waste gas. So it is absolutely important to have sufficient oxygen with proper mixing within the chamber. And that mixing can be achieved by the spin of the burner flame or the injection of the waste gas. A lot of different special items there.
So we should call it the 3 T's with O2, as you say. Typically, we talk always about the 3 T's, but you are absolutely right, Tim. We have to call it the 3 T's plus the OT, O, or whatever we want to call it. Yeah,
that's a good point, Jochen. They call it the 3 T's of oxidation, but those are the 3 T's, but you need oxygen.
Yeah,
the oxidation part.
And it's different from burner to burner also about the turbulence. Turbulence is something you can't measure. Turbulence is something which comes in from design. All these 3 T's come in from design. Only the oxygen and the temperature is something you measure, but only the oxygen is the one you can control. So we want to emphasize on the O2.
It's absolutely critical. If you have all the 3 T's without oxygen, you wouldn't get full oxidation. you might have some other concerns. But great point there, Jochen. Now, for basic operation, we'll just go through this very, very, very briefly. But when you think about the basic operation, a simple thermal oxidizer would have some type of burner flame. Okay, it could be the burner could have a flame tip where the flame is anchored, or it could have a refractory baffle that the flame sits on. But in either case, there's a flame. That's part of the thermal oxidation process. With that, you have to introduce waste in some way, shape, or form. So the waste can be either injected through the burner, if it is flammable, or if it's inert, it could be injected through a nozzle separately. So in this case, it could be injected through a nozzle. And designed properly with sufficient turbulence and to interact with the flame. But once you have that, you may need additional air, because you can't put all of your air through the burner in some cases. So you might need additional secondary air to achieve a 2 to 3% excess oxygen level. And obviously you also need some type of thermocouple at the end to measure, make sure you have proper temperature within your combustion chamber. So the excess oxygen measurement adjusts your secondary air, which we'll talk about later. And then you operate sufficiently at high enough temperatures within your combustion chamber before it vents out to atmosphere. So just like we talked about the 3 T's of oxidation. And then again, if you may need additional equipment. So let's talk a little bit about a multi-stage thermal oxidizer. I won't go into too much detail on this, but I do want to make it clear that a multi-stage thermal oxidizer would be used if you have nitrogen-bearing compounds. Say you're burning amines, for example, or some type of acrylonitrile. It really depends. A lot of different types of applications. In those cases, you operate fuel-rich, and substoichiometrically. So you're starving the flame of oxygen, generally 70 to 90% stoichiometry, generally very high temperatures, 2000 to 2400 degrees Fahrenheit for 1 to 2 seconds residence time. And with that, the burner is designed specifically for this reducing environment. The chamber is designed for these extremely high temperatures. And what you're doing in this reducing chamber is you're turning those nitrogen-bearing compounds, starving it of oxygen so that any nitrogen present forms the diatomic nitrogen molecule as opposed to NOx. So the whole point of a reducing chamber is this diatomic nitrogen. Now, in a multi-stage thermal oxidizer, you would also need some type of quench section, because you can't just emit this producing gas to our atmosphere. You need to do something else with it. So generally, it's followed by like a quench section, and it's kind of represented here, where you would add additional air and additional. You could add water, especially if there's a high reaction after the oxidation air. But you want to create additional hotspots so that you don't recreate NOx. But in either case, you add air, potentially additional. You may also add water, and then you have your oxidizing chamber. And this is the exact oxidizing chamber we were talking about before, where you control it at high temperature so that you can thermally oxidize the remaining waste gas before it goes through the rest of the system and out the stack. Now, the downstream equipment that you might have in your plant can tell you a lot about what you're.
Sorry, Tim, go back for 1 second, please. We say here oxidizing chamber controlled by an oxygen analyzer. Just to be clear, this will require 2 oxygen analyzers, one for the reduction chamber to measure the air to fuel ratio, and the second analyzer is in the oxidizer chamber. I think that's essential to say.
That's a good point, Jochen. So like we talked about before, you would have your excess oxygen measurement here to make sure you have sufficient oxidation air, or secondary air, sometimes we call it secondary air. But you could have a ZIRCONIA oxygen analyzer here. ZIRCONIA has very special properties that'll allow you to measure excess fuel levels, and we have we have different options for measuring excess fuel, which we've done for the glass industry, which we've done for the steel industry. But all of those industries require some type of reducing chamber or some type of uncertain air to fuel ratio mixture. But you could use a ZIRCONIA oxygen analyzer designed to measure excess fuel. I'd have to reiterate that, excess fuel, but you certainly could, and that could help inform you of where you are in your stoichiometric air to fuel ratio, and making sure that you're substoichiometric. But this chamber is certainly designed to specifically be substoichiometric. Good point there, Jochen.
Yeah, and again, let me come back for 1 second. Since there is some confusion about the 25%, this is excess air. If you add 21% of volume percent of air, then 25% of the excess air translates into 2-3% volume percent oxygen. Excess air does not mean percent volume, percent oxygen. It's percent of air injected into the reaction or in the burning chamber.
Yeah, that's a good point. I'm glad you brought it up. Yeah, ultimately you need an excess amount of air.
You need an excess amount of oxygen, but it's not 25%. This is the excess of the air.
But this is
okay. Let's move on.
Yeah, but by the time you get to the outlet of the chamber, after it reacts with the waste gas, it'll be about 2 to 3% excess oxygen.
Absolutely.
So like we were talking about before, the downstream equipment can tell you a lot, and in particular, if you have chlorine, for example, you would need some type of spray dryer absorber or some type of Venturi scrubber like you see here, or some type of packed tower. All of those are different ways that you could handle corrosives like chlorine or sulfur. If you have particulate, you may need a baghouse of some sort with dropout zones and dust collectors to accumulate that particulate before going to atmosphere. You may also need an electrostatic precipitator or a cyclonic separator like you can see here, depending on what else is in your waste stream. You could also consider high pressure thermal oxidizers, which are not very typical, but in those cases they would have some type of pressure vessel design. But a typical thermal oxidizer does not see high pressures because it ultimately vents to atmosphere. But that being said, you can also have other designs, like we saw some examples where the waste was fired downward. Waste liquids would be vertically down fired. Waste water, waste liquid, both of those would be vertically down fired. Even in some cases, if it had particulate, it could also be vertically down fired, just so it could all accumulate at the bottom of the analyzer through a dust collector or dropout zone. And then finally, you could also consider different designs, whether you have nitrogen-bearing compounds, whether that be a multi-stage oxidizer or selective catalytic reduction or selective non-catalytic reduction. But the downstream equipment can really tell you a lot about what's in your process and what's being incinerated. Now, we talked a little bit about this, and I know there were some questions already about the excess oxygen measurement. But this is a really rough piping and instrumentation diagram on a thermal oxidizer. Very rough. I made it myself. So, but if you think about it, your waste gas is either introduced through the burner or downstream. You have your flame here, but how do you control it? And so your thermocouple controls the fuel gas, the fuel control valve. So the fuel that goes to the burner that tells you how much how much additional fuel you're going to add. That's all dictated by the temperature. So if the temperature decreases, you'll increase your burner. You'll open your fuel control valve, and that'll introduce to the chamber, so that you get back up to temperature. If it's too high of temperature, you obviously cut back on your fuel control valve. But when you think about the excess oxygen measurement, that actually controls your secondary air. You want to make sure that you have enough air and oxygen present so that you have 2 to 3% excess on the outlet. The only way that you can do that, in most cases, you can't put all the air through the burner. So the only way you can really do that is by having an additional secondary airstream, the primary being the one going to the burner, the secondary being injected downstream. And so this air ultimately is controlled by the oxygen measurement. And so if you're getting too low of oxygen, excess oxygen level, you will open up that valve, you'll increase the burner, increase the blower capacity, and it'll put more air into the system so that you have sufficient air. So it's very important to have this excess oxygen measurement. Now, I want to make a little bit of a connection to this. So this excess oxygen measurement can be made primarily through a zirconium oxide sensor. And zirconium oxide is a very unique sensor made out of ceramic to measure oxygen. So it's unique in that it has a platinum coating on the sensor's sample side. So whatever sees the sample gas, whatever sees the process gas, and also has a platinum coating on the other side as well for the air reference. And basically, it operates at sufficiently high temperatures, at a constant high temperature, in order to have the physics allow for the oxide ions to travel through the ceramic. That's a different aside, but basically, the physics have to operate at a certain temperature, controlled temperature, and the oxygen measurement is made with the partial pressure of O2 from the sample gas. So whatever's in the sample gas, that partial pressure versus the partial pressure of the reference. So that's the basic of how the measurement takes place, and it actually provides an excess oxygen measurement. So this excess oxygen measurement correlates with the burner air to fuel ratio. So this is an example of what a zirconium oxide sensor looks like. And what happens is, because it's operating with a platinum coating and at high temperatures, the oxygen actually first oxidizes on the catalyst. So the oxygen first oxidizes on the catalyst, and then the oxygen measurement is taking place. So if that makes sense, what happens first is you have the sample gas. This is the outlet. The outlet sees the sample gas. The inlet is the reference. It's a hollow tube. So the waste gas comes to the surface. It reacts on the catalyst, and then the O2 measurement is taken. So only after anything combustible, oxidizes on the surface, then the measurement is taken. So the oxygen measurement is taken after all combustibles are consumed within the process. And we call this a lot of different things. It has a lot of different names in industry. This residual oxygen measurement can be called a residual oxygen measurement. It can be called a net oxygen measurement. It can be called an excess oxygen measurement. But that, because it takes into account all of the combustible compounds in the stream, and because it consumes them all first before making the measurement, it correlates directly with the air to fuel ratio. And this is unlike a lot of other technologies, like paramagnetic or optical, because those would just tell you what's in the oxygen present, but it doesn't have that extra step of actually consuming the combustibles and taking the reading. So when you think about go ahead.
And Tim, I think we have to point out here at that point, there is of course different methods of measuring oxygen in such streams. You can do it with the classic paramagnetic way. You can do it with optical systems. You can do it with electrochemical systems. Why is ZIRCONIA the chosen method for this thermal oxidizers? It's its ability to measure the net oxygen, as you just said. And don't forget, only with ZIRCONIA you can really measure at the hot part of the process. With none of the others, you have that capability. It doesn't work physically or chemically, however you see it from which point. That's a unique feature when you go with ZIRCONIA.
That's absolutely a great point, Jochen. I mean, again, you want to make sure that you can control, close enough to the, within the chamber so that you can control the secondary air. You need to be able to handle that high temperature, the 1650, the 900 degrees Celsius plus, depending on the process. So great point, Jochen. And it is unique.
I hear a lot, why are you doing that this way and this way? So I think today we have so many methods, and we at AMETEK, we can offer you different methods of going from A to B, but we have the luxury that we can choose the best way of reaching the point where we want to get with the best technology for this application. I think that's a key point want to make here.
Thank you, Jochen. Yeah, that's why I'm stressing the importance of the excess oxygen measurement, because the only way that you can really straightforwardly correlate to the air to fuel ratio is through this net oxygen measurement. So good point. And as far as it comes to a thermal oxidizer, where it comes to a thermal oxidizer, considerations around a thermal oxidizer, is that a thermal oxidizer can have very variable waste composition. It can have massive fluctuations. In some cases, it can go from partially flammable to extremely flammable. It could have changes in composition from different compounds, concentrations. There's a lot of different fluctuations a thermal oxidizer can see. So the ability to very quickly detect low excess oxygen levels are important so that you can quickly respond, adjust that secondary air connection. And ultimately, the destruction removal efficiency depends on the excess oxygen level. The only way that you can have, proper destruction removal, 99% removal of the waste gas, is through, the 2 to 3% excess oxygen with that time, temperature, and turbulence to do that. And again, because
one key point you just make, Tim, it's another point for zirconia. It has an unbelievable flexibility when composition change. On optical systems, you have to somehow adjust your system for the composition. On extractive systems, you have to modify your sampling system. Depends on the composition, depends on the state of your sample. With zirconia, it's a kind of in situ measurement. We call it closed couple extractive, but it works under all the different working conditions of the oxidizer, of the reducing chamber. So it offers a wide flexibility, especially for this application.
Thank you, Jochen. So, and that flexibility really plays into the fact that it gives you, basically allows you to control your secondary combustion air with just one measurement, and that's the excess oxygen measurement. So with that, where would you install it? I mean, I know we talked a little about the reducing chamber, with an excess fuel design of a zirconia analyzer, but really, if you're thinking about the oxidizing chamber, you would locate that downstream. So right at the outlet of the combustion chamber. And again, why do you do that? It's the whole purpose is to, again, monitor the excess oxygen level to control your secondary air. When you think about the measurements for a thermal oxidizer, it's absolutely critical to measure excess oxygen for the secondary air control. Again, that relates to your air to fuel, air to waste ratios, making sure that you have sufficient air oxygen present for full destruction removal efficiency, and also responding to any unburnt waste. It's very important that you have the ability to detect unburnt waste, and that's why it's an excess reading, because it's detecting the oxygen after everything else is consumed. So that's just something to point out.
My most favorite topic, combustible detector. Let's not confuse, and as I mentioned earlier, we will do a separate seminar for that. Combustible is something different than CO. CO measures CO, combustibles measures combustibles. And combustibles is CO plus hydrogen. CO is only CO. So I can't repeat that often enough, and be sure we'll do something separate for that.
Right. So I know we haven't talked about it directly in this presentation or part of a combustibles detector, but if your waste, but a combustibles detector could allow you additional monitoring for combustibles breakthroughs. So like Jochen pointed out, we can certainly talk about that in the next presentation. But for this, I want to make it clear. I know we didn't talk about it very much, but for reliable control, you absolutely need to think about how you measure that oxygen. But as far as the combustible detection, combustibles provide you additional information on if you start to get a low oxygen reading. Combustibles can tell you, well, is that because of incomplete combustion? And what are your operating limits? Do you need to increase your air to fuel ratio? So it provides a secondary measurement for safety and to monitor for, is your oxygen level too low? Do you need to increase your oxygen set point, your excess oxygen set point? So this is I won't go into too much detail, but if you think about combustion as two different reactions, the first one, oxygen reacting with the fuel, creates combustibles. The second one being combustibles with enough oxygen go to carbon dioxide and water. A combustible detector will allow you to detect for combustibles breakthrough, low levels of, and inform you on whether or not you need to increase your excess air on the outlet, or excess air or secondary levels. So it's a secondary measurement, but it definitely informs your excess oxygen measurement. And then if you wanted to monitor for safe startup, you could also consider a hydrocarbon or methane detector. So different ways to approach a thermal oxidizer. I know we talked a lot about the excess oxygen measurement because it's absolutely critical for that secondary air control. Combustible detector could be considered for safety and to inform you on what's happening as a secondary measurement point within the thermal oxidizer. Is it combustibles breakthrough? Is it unburnt waste? So that'd be something that you can consider. Now, I want to talk a little bit more with the remaining time. I know we have a little bit of time left. And I do want to answer any other questions you have. So for highly corrosive applications, you do need to think about the analyzer as well, because we've had a customer in the past who was in a chemical plant manufacturing chlorine and chlorinated compounds like PVC and vinyl, with vinyl chloromonomer, and they had a situation where the thermal oxidizers that they were receiving were designed with less expensive 316 stainless steel versions of the combustion analyzer in this highly corrosive application. And so what they were seeing was that the hydrochloric acid from the process and from the products of combustion were attacking the wetted parts of the oxygen analyzer. And so that was inevitably causing leaks. And how do you find those leaks within the analyzer tubing, which ultimately caused concerns with reliability and safety. And so our specific customer had to replace their stainless steel analyzer every 6 months. It wasn't until we got a hold of this information that we were able to work together with them and identify a Hastelloy C option. So at the time, many years ago, we had the WGG4, the Thermox WGG4 flue gas analyzer, and we created a special version with Hastelloy C internals, and that was beneficial for them. It had a longer life, was much more reliable with much less maintenance, and ultimately that chemical plant standardized on this unit. So it absolutely helped them in making sure that they could stay compliant and also stay reliable. Now, we have also more recently adapted this technology in those lessons learned from the WGU4 Hastelloy C special to a WGU5 Hastelloy C option. And so suitable design from all the lessons learned from the WGU4 Hastelloy special, which includes the Hastelloy C wetted parts, flame arresters, corrosion-resistant zirconia oxide cell to ensure that it has proper life, also with a check valve to make sure that gas doesn't go in the wrong direction on the cal gas line. Same with the Hastelloy C calibration gas. A lot of considerations around the calibration line just to make sure it has high integrity. And then we also have Hastelloy C probes and an option for cylinder gas audit software, which we'll talk about that in a second. But I just want to make you aware of that, because if you have a highly chlorinated thermal oxidizer application, you would want to consider what is your analyzer, what's the analyzer that you're using for your excess oxygen measurement, because it should absolutely have some additional reliability and consideration for the Hastelloy C to handle those highly chlorinated applications. So something to think about. I want to make everybody aware of that. And then also something to think about as well. We also offer a special new option for USA specifically on cylinder gas audit software to basically allow you to automate some of the SEMS monitoring systems that you have for your thermal oxidizer. So basically taking that thermal oxidizer application and any of the SEMS requirements on continuous emission monitoring and allow you to have much more tailored design so that you can basically use the WGU5 with its CGA software to automate your clean to gas audit, cylinder gas audit processes. So something to think about, especially if you talked about RADA in the past or if you have those concerns. So it's just something to think about. And obviously, if this would ultimately allow you to automate your process within the analyzer, so you don't have to buy a digital PLC or something like that. So that ideally save you additional money for building. So that being said, all those together, the major takeaways for any thermal oxidizer is to realize that they're not like a fired heater. They burn chemical waste specifically to eliminate them before any of that flue gas is sent out to atmosphere. It's pretty critical that you think about what you're burning, whether or not it's air versus waste, because that absolutely changes the design of the thermal oxidizer. So any thermal oxidizer vendor would need to know that. And more than that, you want to be mindful of if it's not an airstream, you would want to consider your excess oxygen measurement and any type of analyzer that would require, and additional measurements that we talked about as well. But primarily, these thermal oxidizers require the 3 T's of oxidation: time, temperature, and turbulence, at sufficient oxygen levels for full destruction and removal of contaminants. And you want to think about that you'll come across downstream equipment, especially if it has certain waste compounds or high enough heating value for that waste recovery. And then finally, excess oxygen levels, control that secondary air. That's absolutely critical, that excess oxygen measurement, allowing you to have the correct air to fuel and air to waste ratios so that everything is fully oxidized and that you can control that secondary air level accurately. And then finally, you want to make sure that you have proper considerations for chlorinated applications, corrosive applications, and like we talked about with the Hassel-AC internals. So all that being said, I appreciate your time today. I hope this was informative and educational because there's a lot of things to think about within thermal oxidation, and I don't think it gets enough attention in the process world. So that being said, I definitely welcome your questions. You're welcome to put your question into the chat and let us know if you have any specific questions. I'd be happy to answer with Jochen here.
Yeah, I think I have answered some of the questions already in the chat window while you were talking. Of course, there's always some very specific questions, and Tim and my colleagues will get back to you individually and have a separate discussion for more detailed, as we can go in detail in a limited amount of time. So
yeah, thanks for going through the chat.
Thanks for listening.
So John, any other questions that you identified or things that you want to point out?
No, there's a number of questions, as Jochen just mentioned in the chat. Some are fairly specific, so I think I agree with Jochen. We have the contact information for those that asked that question, so we can reach out to them directly and have more detailed discussions around that. Tim, there was a question just around the components and mainly the analyzers and their certification for hazardous environments. So I don't know. I know we have a wide array of combustion analyzers, but I don't know if you just want to touch generally on that, perhaps in the few minutes we have left.
Yeah, I see that in the chat on hazardous area certification. The short answer is it really depends on the application. I can think of examples where general purpose was suitable, and I can think of examples where it required hazardous area class 1 div 2. So it really depends on the application. So whether that be zone 2 in ATEX or IECEX or class 1 div 2, it really depends on the application and what's really around the thermal oxidizer. That's more what it is than anything else. What's around it that would classify it as class 1 div 2 or something else.
Okay.
Good question though.
Well, yeah, it is a good question. So we're right at the top of the hour. So I do want to thank everyone again for attending today's session. We hope you found the content informative. I would like to thank both Tim and Jochen for sharing their expertise on thermal oxidizers. I did post in the chat just some links to products as well as the links. If you don't know who your local contact is, that link is in there as well on the information related to today's presentation. As I mentioned, we are recording this session. We will post it on our YouTube page in the next 24 to 48 hours, and we will reach out to those with some of the more detailed questions separately. So thank you again for attending, and I hope you enjoy the rest of your morning, afternoon, or evening. Thank you.
Thank you.
Bye-bye.
Okay, thank you. Goodbye to everybody.